Okay, let's get started. Welcome back, and we're sort of transitioning a little bit of a topic here. So one thing to keep in mind as we start to talk about pipelined architectures, and we'll work our way to it here, uh, is that in the lab you're still going to be implementing your single cycle processor. So when you want to look for what's the closest thing to a guide for what you're doing in lab, that would be those early sections of chapter 4 and last week's discussion, last week's topic. And I think we did discuss what I would consider the general design philosophy you have to follow for project part B. You just have to do more of it for project part B, and that's the main challenge in working with the test framework for project part B. As we ease our way into pipelining here, we will also be working on a pipeline implementation for project part C, but that's not still for a few weeks. So we're getting a little bit misaligned here, but the core concepts are still very relevant to what you are doing in the lab. A very minor administrative note, I posted this in Discord. We're a couple days behind, which is fine. There's no requirement we get to exactly this number of topics at the end of the semester. But I have a quiz, which is a perfectly easy quiz, but will only be easy after Wednesday. So I'd like to push that quiz to Friday instead. You're still very welcome to attend on Wednesday as well and learn, the more pipelining topics on Wednesday. But the quiz itself will be on the first few minutes of Friday's class. So also come back on Friday as well for that next quiz. So we already briefly introduced this high level topic on Friday, um, and with a little bit of the bookkeeping notes of where this is in the textbook and what's coming up in the course. We're actually going to introduce this somewhat middle topic referred to as multi-cycle data path and control first. Um, we're going to be relatively quick with this topic for a couple of reasons. First off, because the book doesn't cover it all that well. It's in the appendix and it's only kind of sort of in the appendix. And so actually these notes will probably be the best reference you have on it. It's also a topic that is really just a bridge topic, and it's not something we're going to be implementing in the lab either. So that'll be primarily today. We'll talk about the multi-cycle processor implementation, and then we'll move on to what's those next sections in the textbook, which is the pipeline processor design. And we're going to kind of take our milestone mid semester checkpoint at that point after this Friday's coverage of pipelining. And I know that when Friday comes around, there'll be a lot of questions I think that'll come up with regards to, well, if you pipeline, isn't that going to cause problems with X, Y, and Z? And wouldn't this add some additional logic that we need to really think about? And all those questions are valid. We just won't have gotten to those yet. So in terms of our checkpoint, it'll really just be a conceptual introduction to pipeline processor design and control. And then we're going to move on to how do we actually handle that in practice? What are the edge cases that make that a fairly challenging thing to implement effectively? But that won't be part of that checkpoint. So that won't be part of the upcoming midterm that we have next Wednesday. We'll have a review session again on Monday. The main takeaway with regards to midterm number 2 or the second exam this semester is it should look very similar in function to exam number 1. I'll just make sure I have the Canvas timing of the quiz more properly sorted out so we won't run into that headache that we had for the first exam. And there's Yoda there to inspire you, whatever he says, right? Do or do not. There is no try. So just do it. You'll be fine. It takes prep. You know what the type of questions that we're having on quizzes and on homeworks, and there's going to be more of it, and you're going to be just fine. But you do have to prepare for it, and I know everyone can do it. And hopefully, as this material connects more closely with also what you're doing in lab, um, all those hours spent in the lab are still beneficial for understanding those type of exam questions you're also going to have to deal with starting on this Wednesday's upcoming test. So another abstract view of what our single cycle implementation looked like. It's a little bit different. You can still see the flow from sort of left to right, from instruction fetch to execution. But this abstract view is kind of viewing the entire implementation as a set of state elements and then separate pieces of logic that help us determine how we transition from one value in a state element to another value in a state element. And again, our state elements is our program counter, it's our data memory, it's our register files. And we definitely laid it out not in this view of things as state element to state element. We viewed it in terms of what functionality is required and what functional units we would need to implement this functionality. But this abstract view is equally valid, which is what are the state elements in your design how do you transition the values in those state elements? And we have a model of computation that's best suited to represent that abstract view of a system, a so-called finite state machine, right? And you can actually think of your single cycle implementation as a type of finite state machine where effectively the program counter and potentially the registers and data memory itself is the state storage. And all of our logic is put in place, all of our combinational logic is put in place to determine how we transition from one state to the next. The reason we don't typically think of it that way is because the state space in this view would be extremely large. All the different potential values of our registers, all the potential different values in our program counters could be thought of as unique states. And it's a very large number of states. If we tried to draw the entire bubble diagram for this implementation, it would be we'd either have to abstract it significantly or it would be significantly large. But conceptually, in terms of the type of circuit we've effectively built for our single cycle implementation with data path elements and control elements and state registers, it is a finite state machine where we take current state and we calculate next state as we update those state elements there. And we also know what is not as correct or efficient or as ideal with our single cycle implementation. We were told, or we set as our primary design philosophy, that it's a single cycle data path. So CPI is going to be equal to 1. It's got some advantages. It's relatively simple to decompose and to understand what is happening. It's something you can build in 2 weeks, in a lab environment. The performance analysis of it is relatively straightforward. Since CPI equals 1, our instruction count, our dynamic instruction count, directly correlates to our resulting performance, and the actual instruction mix is somewhat irrelevant for us. But we can see, at least starting in this slide here, some of the inefficiencies of it. And this goes back to our cycle time, going back to our clock frequency due to the critical path of our circuit implementation. And we've talked about it a few times now that really our load instruction is the one that's exercising all the combinational elements in our single cycle data path. And so our load instruction is the critical path for our implementation, right? Other instructions are going through only certain parts of the design and are able to circumvent others and just avoid going through others. Branch goes through significantly less than the rest. Jump goes through even less than branch. And load is the one that requires us going through every major stage of the design and all of the major functional units that we have there. And that's our critical path, right? That's our definition of the longest path through from register to register in our design. And that limits what our clock frequency can be. And connected to that fact is the realization that clock cycle time is generally thought of as a fixed thing on a per circuit basis. There's overclocking and underclocking and some dynamic frequency scaling one can do. But for a traditional design, that critical path dictates our clock cycle time, and every instruction then, whether it needs that entire time to execute or not, this one would, this one certainly wouldn't, is going to execute in the time associated with the critical path instructions for our implementation. So we have a CPI equals 1 CPU in our single cycle implementation. So each instruction takes 1 clock cycle, but it's a relatively slow clock cycle. That's the main downside of our single cycle implementation, that whatever this critical path works out to be, every instruction is effectively on that critical path, or might as well have been on that critical path, because no matter what, given a fixed clock cycle time, 10 nanoseconds for this path here, every instruction is going to take 10 nanoseconds. We can't generally run some instructions fast for the single cycle implementation and other instructions slower. Our CPU time is going to be effectively fixed from an instruction to instruction basis. And that's what this is kind of showing here, what effectively is a slack involved in all the other instructions as they're being executed on the processor here. The load word is effectively efficient, I guess. It requires that entire clock cycle, and that's illustrating the execution in an abstract way of a load word for a single clock cycle. If our next instruction was a store word, it would effectively get done earlier in that clock cycle, and the remainder of that clock period would be wasted. You can think of it as slack, as time that we're not using in our design. It's part of a clock cycle, and it can potentially be a significant portion of a clock cycle that is not being spent on anything. And imagine you do have a workload in which load word is a relatively infrequent instruction. In practice, it's not, but let's imagine it's a relatively infrequent instruction that we're using here. We would have an implementation in which our clock frequency is set by that critical path instruction, but we're wasting chunks of every single cycle that we have. Whether it can be measured in percentage or measured in seconds is a little bit harder to analyze, but there is definitely that case where there's some waste that we have there. There's also potentially some waste of functional units as well. Because everything is having to be executed in a single clock cycle, we can't really share any resources. That would lead to timing glitches. So every element has to basically be multiplexed via statically generated control. And if we need to access two memory ports in a single instruction, which we do for instruction and data memory, we need two separate physical ports, right? We need two separate physical memories, at least at the abstract level there, so that we can actually access both of those in a single cycle. The upside's still the case. It's relatively simple, it's straightforward, it's a very good baseline for us to compare other implementations to. But the primary downside, beyond just this potential duplication of functional units, is this waste. And not just this waste for one instruction, it's waste for every instruction that's not the critical path instruction that we have there. So when we talk about the multi-cycle implementation, that's what we're talking about here. A way to break that assumption of CPI equals 1 and to do so in a way in which that we're hopefully not wasting any portion of a given clock cycle. So for the multi-cycle implementation, and again, it's kind of buried now in sort of the late appendix in the textbook, but it is there. Instead of each instruction taking one clock cycle, our philosophy is that each instruction step or stage is going to take one clock cycle. And so consequently, all of our instructions are going to take more than one clock cycle. Our CPI is no longer going to be equal to 1. And connected to that is the fact that depending on the number of steps an instruction requires, with load word taking the most number of steps, it's the same reason it was on our critical path before, now each instruction, depending on what the instruction is doing, can take a varying number of clock cycles. That's why it's referred to as multi-cycle, just multiple cycle data path here, where it's not one clock cycle, it's potentially multiple clock cycles. And how many clock cycles is depending on how many steps that instruction actually requires. That's going to change things up a little bit with regards to our implementation. In theory, if we allow now each step to take a clock cycle versus the entirety of the instruction to take a clock cycle, we're carving up our critical path, right? If load word, instead of taking one cycle, now takes 5 cycles, roughly, kind of, sort of, our clock frequency could be close to maybe 5 times faster. This never, nearly works out so neatly and cleanly, but something along those lines is certainly true. That we're splitting the instructions up into multiple steps, putting registers basically to split up the clock cycles for each of those individual steps, and we should have resulting better critical paths and faster clock rates. A secondary advantage of the multi-cycle as compared to the single cycle would be the fact that because our instructions can now take multiple cycles, we don't need to multiplex our functional units in the same way. We don't need to duplicate our functional units in nearly the same way. We can have, for example, a single memory that for part of the instruction can act as an instruction memory, and for another part of the same instruction can act as a data memory. So we actually need fewer data elements here. It is very likely that our total resource usage is going to be less for a multi-cycle implementation versus for a single cycle implementation. The challenge, as we'll see, is now that this is going to effectively be really a finite state machine where we're determining how many instructions or how many cycles we need to take to implement an instruction to execute its functionality, the control logic is going to get a little bit nastier than it was for the single cycle implementation. You may have read or you may have some familiarity with this concept of microcontrol or micro-coded designs at the architectural level, in which assembly instructions are broken down at runtime to much more simplistic assembly operations, these micro operations. It is a very similar concept to a multi-cycle implementation. We have this idea of an instruction that has complex functionality. For the multi-cycle implementation, at least the textbook version, we break that down into a finite state machine. For the so-called micro-coded implementation, micro-op implementation, we break down those instructions into even simpler assembly instructions that can be executed very efficiently. They're very similar concepts. at some point, our instructions get complicated enough that this finite state machine based approach becomes intractable, just the number of states we would have to support. So we wind up writing mini assembly programs to implement our more macro assembly instructions. For this class, given the design of MIPS, we don't have to really go to that level and do that. Each instruction can be broken down into 5 steps or fewer. That's not going to be too many states in our FSM based implementation. So let's see if we can figure out a little bit of the idea just by looking at the data path for the multi-cycle implementation. At the very least, you should be able to look at this and say, this is different than our single cycle implementation. That's a good starting point, at least, that this is different than last week in terms of what functional elements are there and what state elements are there. First off, you should notice there's just one memory module. That memory module is not tagged as instruction or tagged as data memory. It's just tagged, this is our memory module. And as I mentioned just previously, it's going to allow us, because each instruction can take multiple cycles, we can time multiplex whether it's acting as an instruction memory or a data memory as that instruction itself is executing. Same with our ALU. If we go back to the single cycle implementation, we had the main ALU, and then we had a bunch of these little adders scattered throughout the design. The reason being is we needed the main ALU to do our main ALU stuff, to do our R-type instructions as well as some potential other arithmetic operations. And then we just had a need for other, usually adder circuits in our design, right? We had a need to do PC plus 4, as well as PC plus branch target offset in our design. And because the ALU was already being used for those same instructions, we had to instantiate different little adders for your single cycle data path. That doesn't need to be the case for a multi-cycle implementation because the instruction can take multiple cycles for a single instruction. We can just reuse those elements. And that ALU, for instance, can be used to calculate PC equals PC plus 4 in one cycle. And then in a follow-on cycle can be used to calculate add T1, T2 with regards to the instruction's actual functionality. And so what you'll see for the multi-cycle implementation, and we will talk about this and compare and contrast this to the pipelined implementation, we're breaking down a single instruction into multiple cycles, but there's still a pretty big dependency there. And so we're not going to be overlapping instructions, at least not yet, with regards to this breakdown here. Each instruction is going to take 3 to 5 cycles, but in saving on these functional units, that also limits our ability to overlap instructions. We have to hang on to this memory because it may be necessary as a data memory later in the instruction's execution. We can't use this as an instruction memory for the next instruction until the previous instruction is completely finished and executed. So that's the first thing I think you should see, is that there's just less stuff going on in this diagram than the single cycle version. There's less things that we need in terms of functional units because we can do a better job of reusing our functional units than in the single cycle implementation. What there are now instead are these additional, we'll call them internal or call them state registers in our design that are there to store sort of the intermediate outputs of our functional units so that they can be used in subsequent cycles. We can start to get the hang of it, I think, just by looking at it, just via the names here. We still have the program counter, but for example, now we also have an additional register referred to as ALU out, which is hanging on to the result of our ALU operation. Because for certain instructions, such as, for example, the load word instruction, the result of the ALU is needed in a follow-on stage of our instruction's execution. If it all fits in one cycle, there's no harm, right? We just make sure we have wires connecting everything up in muxes as needed, and we take as long as it requires to finish up that cycle. In our multi-cycle implementation, the design philosophy is split that up into multiple cycles, split that up so that it's going to take one cycle, then a follow-on cycle, then an additional cycle to execute a given instruction. So we need ways to store that intermediate result so that it's still valid from one cycle to the next. And that's what we need flip-flops to do, right? That's what we need our registers to do to hold state of our processor's implementation. So there's going to be fewer functional units here, but more state elements here. And kind of like the program counter, when we think of that as a state element in our design, this is something that is effectively going to be transparent to the programmer. This is called the instruction register. This is not something that, without some additional special architecting of this system that's not evident here, is not something that as a programmer you would have access to. It's not part of the register file, just like the program counter in MIPS is not part of the register file. It's holding intermediate state for correct execution of a multi-cycle data path for a given instruction, but it's not part of the software accessible, the user accessible processor state. So clocking wise, this isn't necessarily any different than before, except that now that we have all these additional state elements, we're going to need additional control signals to keep track of when and how we should be writing to these state elements. We already have control signals corresponding to our register write signal for our write signal for our register file. We already have control signals for our data memory write enable. We're going to need additional control signals for which we didn't have before for our program counter write enable. Right? For the single cycle processor, we didn't require that. We didn't need a write enable for the program counter, because no matter what, in every single instruction we wrote to the program counter. In your implementation, you can put in a write enable for the program counter. If you use your n-bit register component that we started with earlier in the semester, it has a write enable port on it. You might as well have it there. But for our single cycle implementation, every cycle we write to the program counter. There's really no need, or you can hard code the write enable to 1. Now for our multi-cycle implementation, we're only going to be writing to the program counter once for every given instruction. And since every given instruction is going to take a varying number of cycles, we now need a proper write enable control signal for the program counter, as well as for these other internal state registers. We need to write to them when the instruction requires it, and they're not going to require it every single cycle. For a typical instruction, we write PC equals PC plus 4, right? We only need to do that once for a given instruction. And if the instruction takes 5 cycles, then for 4 out of every 5 cycles, that program counter's write enable should not be set to 1, it should be set to 0. So that's when I talk about there's additional control required here. And as we visualize it as a state machine, that's what the state machine is doing. That's our Mealy state machine logic, which is from state to state, what are the values of both kind of the traditional control signals that you're already aware of, that you're already building for project part B, as well as the control signals that are specifically in place to update or not update our state registers. Total hardware usage is still probably significantly less than for the single cycle implementation, but the actual inputs to our muxes and the amount of control signals being generated is going to be larger for the multi-cycle implementation. So again, this is the multi-cycle approach. We're going to break up each instruction into multiple steps, where each step takes a clock cycle. The reason this concept should not be, it is different. The reason it shouldn't be terribly overwhelming to you is because the steps are still the same. The steps have not changed. And even as we go into the pipelined implementation, the steps still have not changed. For a load word instruction, the things we have to do to execute our load word instruction does not change at all. And so don't forget that as you're worrying about the details of an implementation of single cycle versus multi-cycle versus pipelined implementation. Load word still has to do the same exact things that the MIPS spec says it has to do. Don't forget that. The difference now in our multi-cycle implementation is those steps, where and when it's feasible to do so, are split across multiple cycles. And we're doing so conceptually in order to improve our critical path, to attempt to roughly, and it's always very roughly, balance out the amount of work required for each cycle. And hopefully our clock cycle time, given that there's 5 major steps of our load word instruction, hopefully our clock cycle time can roughly be a factor of 5 better, improved. That's all very rough, and it's very hard for us to say for certain. We've just so happened to split things up into a factor of 5. But if you look back at the original MIPS, the papers and the original justification for the 5 major stages of a load instruction, they were attempting, at least based on the implementation technology at the time, to roughly partition it into fifths, to roughly get a 5x clock frequency than what would otherwise be possible. So unlike in the single cycle implementation, where at the end of a clock cycle the instruction is done, at the end of the multi-cycle implementation, at the end of a cycle in a multi-cycle implementation, a particular step is done. And that's what those additional registers are there for. And these are their names. So there's a register that holds the value of the instruction we wanted to read, because we may need it for multiple cycles. There's a register that holds the value read from the data memory, because we may need that for subsequent cycles. Likewise, there's a register that holds the result of reading from the register file, which sounds a little redundant, but then as we see how it's used here, it's actually not redundant. That's just referred to as A and B. Reg file read 1, reg file read 2 maybe would be a better name, but the textbook refers to them as A and B. And as we already mentioned, there's a register to hold the result of the ALU output computation. And our control logic is set up so that we're feeding the inputs to those registers, we're optionally, if needed, storing results into those registers, and then we're using the values in those internal state registers to feed into the inputs for the next stage of an instruction. But as we talk about this, I just don't want you to forget that, because it is new, it is different. It's not something you've looked at before. It's the same steps. An add instruction is doing the same exact things it's doing in your Project Part B implementation, what we were talking about last week. We're just breaking it up into multiple cycles. And because we're breaking it up into multiple cycles, we can reuse functional elements in a significantly different way. And we have to store the results of computations across multiple cycles. So let's take a look at how we could do that control in an FSM approach. Our quote unquote fuller data path, and I would acknowledge that this is just kind of given to you in the textbook. To the extent also you could argue that the single cycle data path is also kind of given to you, but the difference is that one, it's kind of staged over time to kind of explain the design decisions along the way. For the multi-cycle data path, it's just kind of a given. Here's how we do the multi-cycle data path. This is not the only way one could build a multi-cycle data path, but it's logically consistent with the design that went into the single cycle data path. There's a lot now going on in here that wasn't in the previous slide, right? The functional elements are still the same. The state registers are still the same. Some of the muxes we have in the design are similar to what they were before. We have our register destination mux that's here. This mux, although it doesn't look like it, is our, what did we call that one? Mem to reg mux from the single cycle implementation. It's doing effectively the same thing. Our ALU now has a lot more muxes or mux inputs for the individual ports because our ALU is being used for a lot more now. So in your single cycle implementation, the ALU was being used for register plus register, or register op register, or register op immediate is what it was being used for in the single cycle processor. Now we don't have any of those additional little adders throughout the design. The ALU is responsible for anything that requires math in our instructions execution. So there's going to be more inputs associated with each of the inputs to our ALU here. Likewise, our next PC value is arguably a little bit simpler than it was in the single cycle implementation because we don't have these additional adders here. We know that either the result as it gets updated is going to be the result of an ALU computation, or it's going to be result of a jump computation. Those are really the only two scenarios now. Branch is just going to be a special case of PC equals PC plus 4. And so thinking of PC equals PC plus 4, you can see this hard-coded 4 as a potential input to this mux. And maybe you can see already that that's what that's going to be for. We don't have a separate PC up counter adder in this design anymore, and we don't need one. Our instructions are going to be taking between 3 and 5 cycles to execute. And in one of those cycles, we should be free to calculate PC equals PC plus 4. And arguably, we can do it in the first cycle. We don't even know what the instruction is yet. We might as well calculate PC equals PC plus 4 using the ALU that we have available to us here, because it's not doing anything else yet. That's our time multiplexing approach. And so these additional control signals are effectively for that. It is more of the same. And so it's following the textbook single cycle view of what control should look like. There's just going to be more of it here, because these units are acting in different ways throughout the instructions execution. We're covering a lot here. let's take a pause. I feel like I'm speaking a lot, and that's fine. There's a lot to take on here. This is a significant change in how we're implementing our processor as we expand beyond just single cycle implementation, beyond just CPI equals one implementation. Couple of the questions I see in there sounds like people who are asking those questions are understanding it. So um, I don't know about simple or more complex are kind of undefined terms in this context. There are fewer functional elements required would be the correct thing to say. I would say about the multi-cycle implementation. Just one ALU, for example. Just one memory module, for example. The control is definitely more complex. Overall hardware resource usage should be lesser in this implementation than in the single cycle implementation. We can also say our clock frequency should be higher in this implementation than the single cycle implementation. If it's not going to be higher, there's no point in doing this whatsoever. That's the primary motivation of splitting up our instructions into multiple cycles, is to improve our critical path. So we can assume that that's the case. Um, and then the main complexity implementation is in the control scheme, in which we have to think of not just a static control, which is look at opcode and here's all your control signals. We still have to do that, but now we also have to look at opcode and understand the main stages of that instruction and generate control signal over a period of multiple cycles. So this control logic now is going to be a state machine, or the next state logic for a state machine. It's possible we just cover this today and then you kind of absorb it between now and Wednesday, and as we jump back into it on Wednesday, um, we'll have some more questions. This topic is a little frustrating, I would argue, because you're not going to be doing it in a lab. So it's maybe a little bit harder to get really, really motivated to work on that there. If you're not working on it in the lab, it's hard to care about the low level implementation details. Whereas for the single cycle processor, I understand that that is the case, that you care about the low level implementation details because you have to do it. You have to get it working yourself. Um, So this is just a summary of what I was talking about here. We have additional multiplexers and inputs to existing multiplexers because we're time multiplexing those functional units in a way that we weren't before. So those inputs to the ALU are the most obvious example. The inputs to the program counter is an additional example. And the inputs to the memory is an example of what wasn't needed for the single cycle implementation, which is depending on what stage we're in, we have to have different inputs into those functional elements there. So these 5 instruction steps, I'll say it again, are the exact same. They have not changed. We've been using kind of the acronyms for them of the various stages that are part of our implementation. These are the exact same. So don't think of this as a new topic, right? From instruction fetch to decode/register fetch to execution to memory stage to potentially a write back stage to our register file. Those are the 5 steps. They have not changed from our single cycle implementation. All microprocessors basically have those 5 stages. The implementation differences are just how many cycles we have to spend per each stage. For the single cycle implementation, all of those stages get squished together into a single cycle, okay, based on the name there. For the multi-cycle implementation, every instruction requires to be fetched. Every instruction requires a decode/potential register fetch. And then every instruction, depending on, you could potentially jump into 2 cycles here, but every instruction has to kind of finish its execution. So every instruction in the multi-cycle implementation is going to, I don't know what's going on here with the video. Every instruction in the multiple cycle implementation is going to take between 3 and 5 cycles. They're going to take at a minimum 3 cycles here. And we have to determine at runtime. I have no clue what's going on with that. We're going to take at a minimum 3 and potentially as many as 5. This is an epic effect. Let's keep it going. I'm just going to disappear. Thank you. I'm gone for the rest of today. You will just hear me and not see me. So step 1 is instruction fetch. which we know what that is. It's the same as it is for our single cycle implementation. But let's cover it slowly because we have to then also understand what does that mean for this new data path. Um, Using that kind of textbook register transfer language representation of what instructions are supposed to be doing, for the multi-cycle implementation, we can definitely break down what has to happen in this instruction fetch phase. We have to use the current program counter value as an address into memory. We have to then load that instruction from memory. And unique for the multiple cycle implementation, we have to actually store that in that internal state register. Again, in the single cycle implementation, we don't have to do that because it's all going to be finished up by the end of the cycle anyway. So we can just store the instruction as wires in our design. There's wires floating through the design. For the multiple cycle implementation, we have to know the value of that instruction for potentially multiple cycles. So that's what that IR register is there for. And then, although it's not necessarily the case that it has to be done in this first step, we might as well do it in this first step. That no matter what our instruction is intending to ultimately do, there's no harm in calculating PC equals PC plus 4 at this early stage. All very funny, guys. Okay. Well, now it's back on to you here. This is our data path for that first stage, where I've just basically circled what is happening for the control scheme. And again, this is different. I want you to think back to what you're doing for project part B, which is you're statically calculating control signals based on opcodes and optionally, for those function codes that you have there. This is definitely different. This is a multi-cycle control scheme in which for cycle 1, you're already calculating control signals. You have no idea what the instruction is yet, but we're calculating control signals because for every instruction, we already know something of what the data path should be doing. Some of these are obvious. Others we can spend a little bit of time discussing what they're trying to do here. For example, we have a control signal referred to as PC write. PC write is a write enable for our program counter that we didn't actually need before in our single cycle implementation. And we didn't need it before because we always wrote to the program counter. Yes, as I mentioned, you could have still a PC write signal, but it would always be set to 1 for a single cycle implementation. In this case, though, we may want to write to the program counter 1 or multiple times in a given instruction's execution. We're saying that in the instruction fetch stage, we just want to write PC equals PC plus 4. So we would set this to 1. That's what that circling is implying here. So that we have our write enable set for our program counter. What are the actual values being written to on our program counter? Well, we have to be a little bit careful here of what's happening. You can trace the signals through your design, and here labeling your signals a bit better will help you as you're designing something comparable yourself. We're taking the current value before it's been updated of the program counter, and we're connecting that to our ALU. And that signal is ALU source A. Again, those aren't great names, but that's which potential input is being fed into the first input port of our ALU. In this case, it's the program counter being fed in. For ALU source B, here's that hard-coded value of 4 again. We're connecting that to the second input port of the ALU. This is the weird textbook ALU control scheme that is not super important. It's an add, right? That's just what we need to encode it as. That'll be different depending on how you did your project part A. That's our add operation. We're calculating PC equals PC plus 4. And then we're connecting that back as the next PC source value that we have here. Similarly, we have a separate control signal referred to as I or D here. Is memory acting as instruction memory or is it acting as data memory? In this case, it is acting as instruction memory. So the address we're actually connecting to our memory module would be not the base plus constant offset load slash store word address. It would be the program counter as an address into memory. Mem read isn't so important for our implementations, but what is important for our multi-cycle implementation is we then actually want to make sure we hang on to that value of what got read from the instruction memory. That's the logic layout of what's happening for the first stage of an instructions execution. We can start to build up what the state machine winds up looking like as well. Doesn't look like much yet because um, it's just one state so far, so it's just kind of this bubble in isolation. But it is a state machine, right? Where the next state is going to be dictated by the current state as well as some inputs coming into the current state values in our design. This is our kind of starting default state. And we can tag all the control signals, again, not statically for an instruction, but control signals that are generated on a state by state basis. So when we're in the instruction fetch state here, those would be roughly the values of our control signals. So instruction fetch doesn't have a lot of decisions associated with it. And the same is the case for instruction decode slash register fetch as well. There's a couple things we can do in this stage. We don't actually know yet what the instruction is. We haven't completed our instruction decode, but there's no harm in reading from our registers. Our RS address in the register file, our RT address in the register file, read them in case they're needed. And similarly, we have the ALU. We don't know really what to do with it yet for our actual instruction. We might as well potentially determine if it just so happens to be a branch instruction, have that branch target address ready to go. And again, this is that RTL kind of pseudocode format, but that is exactly what we would need to do, right? If it happened to be a branch instruction, we'd take the immediate field of our encoding of our I type instruction, shift it to the left by 2, and that's not a minus, right? That's just sign extend as an operation, and then add that to the PC plus 4 value, which is actually what's currently stored in the program counter. So in this stage, we're still not doing any control that's based on what the instruction actually is. We're just kind of getting ready and preparing in case. So we're reading from the register file. So there would need to be some write enable control signals for A and B here. We're also calculating our branch target offset because why not? Let's do another add operation. We still don't know what the instruction actually is meant to do yet. If it so happened to be a branch instruction, we would be ready to go. We would have the result for what the next PC should be in case the branch would need to be taken at that point in time. And from a state machine perspective, it's still not a terribly interesting state machine yet because it's kind of a direct connection from cycle 1 to cycle 2 or stage 1 to stage 2 here. We do our instruction fetch, which corresponds to a series of operations. We're now doing our decode stage where we're really just getting prepared, arguably, right? But the nice thing now is that once we're at the decode stage, we've decoded the instruction. We should now have all that static instruction level knowledge that we kind of assume is already available for us in the single cycle implementation. Now, when we go to that step 3, it's going to depend on what the instruction is actually meant to do. So there's going to be some branches or some multiple edges in this state machine diagram here. Now, depending on what the instruction actually is, what our opcode actually is. So, for example, what the ALU would need to do would really depend on what the instruction type actually is. If it's a load word or store word instruction, we still need to go through and calculate what our data memory address is going to need to be. If it's an R type instruction, there's no harm in what we calculated in the previous cycle, but we still need to do our R type operation. That's our A op B operation there. Whatever it's needed is what we would need to compute at that point to be stored in that ALU out register we have in the design. If it's a branch, well, the nice thing is we've already previously, in the previous stage, in the previous cycle, calculated what the branch target would be. So now we would just need to use the ALU for that equality operation, right? The textbook is really only supporting branch equal. If you were also supporting branch not equal, it would just be a slight variation on that, right? It'd be just an extra mux of, do we care if the result is 0 or do we care if the result is not 0 in our ALU? But the nice thing is because we've already done the branch target address calculation, we don't need to do any additional math there. We would just set the program counter and set the write enable for the program counter to what the value of that ALU out already is. And in this case, if it's a jump instruction, there isn't that much we have to do. We just have to update the program counter value with that jump target address, which is a slightly different calculation, which we don't use the existing ALU for. It's just a wire remapping of the immediate or the J type field in our instruction to the lower 28 bits of our program counter. Again, and I said this enough times now, the stages are still exactly the same. So for your single cycle implementation, we're still doing exactly all these things as we go. The difference is you're doing it all in one cycle. And so, as our control strategy, we basically support all these potential operations and we use muxes to dictate what the actual inputs to our functional elements are going to be. For the multi cycle implementation, we can actually determine what operation is needed and store the results in an intermediate register instead. So now what this third stage looks like really depends on what operation is being decoded at this point and being executed. If it was a load word stat slash store word operation, it would look a lot like your load word store word in your single cycle implementation. We would now take that stored value of A, and we would now take that sign extended 16-bit immediate for our input B, and we would do the add operation for it and store the result here for use in the next cycle. And from a state transition perspective, now it does depend on what your opcode was. We always instruction fetch, that takes a cycle. We always instruction decode, that takes a cycle. Now, depending on what our opcode was after our decode stage, we're doing potentially significantly different things in the execute stage, depending on what the opcode was. And we can kind of just finish up what else is happening here with regards to our total state machine for it. Instruction fetch, and you can correlate this directly to the diagram on the previous slides here. We're always doing instruction fetch. We're always doing instruction decode. Depending on what our opcode is, we're always doing an execute. Depending on what it is, for certain instructions, we're done at that point. Based on this layout and this micro-coded implementation here, if it's a jump or if it's a branch, at that point we're done. We either take or don't take the branch. And if it's jump, we do take the jump and we make sure we write to the program counter. And we're done. And we go back to this stage and we do it all again for whatever happens to be the next program counter value for that branch to or jump to value. If it's a R-type operation, we're also very close to done. We can go straight to that write back stage here. Set reg write with our given register destination that's statically determined from the instruction. We're not updating the program counter. Just go back. You're done after that fourth cycle. For store word, we're also done in that fourth cycle. We're just writing to memory instead of writing to the register file in that fourth cycle. And here's our load word on the left-hand side here that has the 1, 2, third stage where we calculate an address, now a fourth stage where we read from our data memory, and then finally that fifth stage that we're writing back to the register file at that point. Let's leave things here for today with regards to the multi-cycle implementation. It is a little tricky in terms of, we're not directly implementing this in lab. What I think is more important is understanding the design trade-offs involved in single cycle versus multi-cycle. The differences in our critical path, the other major differences in our ability now to reuse our functional elements. On Wednesday, as we jump into the pipelining topic, we're going to attempt to get the best of both worlds with regards to splitting up our critical path and also getting a relatively good CPI value. Because as we'll look at on Wednesday, yes, this is a different way of implementing our data path for the multi-cycle versus the single cycle. If I were to ask you which one has better performance, well, the answer is almost always it depends in this class, but it really does depend, and it's very hard for us to look at a multi-cycle implementation and say that is a better performance decision than the single cycle equivalent. We've improved our clock frequency, but we've also increased our CPI from CPI equals 1 to CPI equals somewhere between 3 and 5. So we'll look at that from a performance analysis perspective on Wednesday and use that as our motivation for why pipelining is a sort of a nice best of both worlds approach. It comes with its own complexities. We'll start to get into that, but that won't be until after next week in any case. Let's leave things here for today. I'm glad everyone had fun with my technical difficulties along the way, as is always the case. And let's pick things up right where we left off on Wednesday. with our quiz being pushed to this week, Friday, not Wednesday. Enjoy, and I'll see everyone then.